internship for the last 6 months, and she actually came here with absolutely no experience doing epidemiology, but was just interested in it, and had the idea that maybe she could come here and hopefully learn something. So I guess you'll see the a little bit about what she's learned and the project that she's worked on while she's been here. So, Elise.
Welcome, everybody. So the study we did is mostly on traffic-related air pollution and lung function. This focus is mainly on children. I'm going to talk about that later. Every year, about 3.2 million people die from air pollution. There are various sources that create this air pollution. Put it down?
Yeah, right there. Right
okay. Is this better? This better? I don't know. Yeah, this is better? Okay. You want me to start over or it's okay? Start again. Well, again, hi everybody and everybody online. And so I'm going to talk about traffic-related air pollution and lung function, and the focus is mainly on children. We're going to talk about that later. So 3.2 million people a year die from air pollution. There are various sources that create this air pollution. This could be burning of biomass or coal, industrial sources, or wind-blown dust, and of course, traffic-related air pollution. Some indicators for traffic-related air pollution that are used are NO2, which we are going to talk about the rest of the presentation, nitrogen oxide, PM10, PM2.5, and black carbon. Besides mortality, some other health effects have been related to traffic-related air pollution. For instance, respiratory disease, cardiovascular disease and mortality, cancer, and adverse pregnancy outcomes. Although there have been suggestions for this relationship, a lot of these health effects need further research. The respiratory disease, asthma attacks, the onset of asthma in children and adults, COPD, and allergy have been linked to traffic-related air pollution. An example of one of these studies is one by a former student here from 2010 who related the incident of asthma to traffic-related air pollution. They found that in Canadian children, the incidence of asthma is increased by 1.2 times for every increase of 10 micrograms per cubic meter of NO2. So as I said before, we're going to focus mainly on children because they're a sensitive group. They're sensitive because they spend more time outdoors, they are more active, have higher ventilation rates, and are developing. And it is therefore important to focus our research on them. Well, another health effect that has been related to traffic-related air pollution is lung function, which we focused on. And lung function is measured by spirometry, and we're going to watch a little video about how they do that. See if it works. I don't know how to put it here. We don't hear the sound. Well, you see this girl, and she is going to blow into the tube. And she first has to slowly breathe in and out, and then she has to do one push, has to blow out her air very forcefully and fast, as fast as and forcefully as she can. And you can see they make a sort of game out of it for children. And she has to hit the balloon. And afterwards, she sort of explained how she wasn't scared, and that if you ever do it, it's not very scared, but the last time the hard blow is kind of hard. And, and she says it's kind of fun with the balloon. So you don't have to worry if you ever do it. Okay, so with lung function is, as I said, measured by spirometry. You have to forcefully exhale. In this diagram, you see a flow chart. And the top half of the graph shows exhalation and the bottom half inhalation. The amount of air you can blow out in 1 second is the forced expiratory volume in 1 second. And everything you blow out afterwards, which was the hard part for her, combining together with what you have blown out in 1 second is the forced vital capacity. The ratio between these two is often clinically relevant because a lower FEV1, which means you can't blow out as much in 1 second as anyone else would in comparison to your total volume, means that there's probably some sort of obstruction in your airways preventing you from exhaling easily. So in children, which are an important group, lung function is still developing. From birth until early adulthood, lung function grows until it reaches its maximum, and then it starts to decrease with age. This is the lung volume in Canadians. So you can see that at the beginning it sort of goes up, and this is stronger for males than for females because they often have bigger lungs because they're bigger and taller. And then it sort of reaches the plateau phase and then starts to decrease with age. Lung function, traffic-related air pollution has been linked to lung function growth, but also with an increased decrease of lung function and aging. For instance, this study, and that is important because, so at first you can see it in this graph. This is for smoking, but the same could be applied for traffic-related air pollution. You start with your lung function of 100% when you're an adolescent, and then your lung function decreases with age. But if you're exposed to, for instance, traffic-related air pollution, your decrease may go faster, and you reach critical levels faster than you would if you were not exposed. So this could be, well, very important, of course. As I said, there's some previous research already done to the relationship between lung function and traffic-related air pollution in children. This research is both cross-sectionally and longitudinal. An advantage of longitudinal studies is that you have multiple measures of lung function over time, which allows you to calculate the growth and if the growth is affected, so this part of the curve. And these measurements are done in the same individual, which makes it strong. So we're going to discuss some of these studies that have been done before. First, one by Brunegreef et al. In 1997. They researched the influence of the proximity to the source in Dutch children. You can see that children who are living close to a highway, that with increasing truck density, their lung function goes down. And a study by Schwartz that looked at the level of exposure. They also found a high association between NO2 exposure and increased NO2 exposure and decreases in FEV1 and FVC. This study also suggested, was the first to suggest a threshold for NO2 at 75 micrograms per cubic meter. So you might be happy to know that Vancouver is below this value, so you're safe for now, or maybe not. We'll see. Then another cross-sectional study by Oftedal et al. In 2008 in Swedish children. They looked at the timing of exposure. They compared early life exposure to later life exposure. As you can see, most of the results, again, show a negative trend, so a decrease with increasing NO2. And this effect was stronger, and they found an effect stronger for boys than for girls. Then the longitudinal studies, which are arguably more important because they have multiple measures of pulmonary function over time. So they look at lung function growth. This study by Schultz et al. In 2012 compared the lung function in children from age 0 to age 8 and compared this for early life exposure versus later life exposure. But this is in PM10, note that, so that's important. And you can see that the black dots are early life exposure and the white and the gray is later life exposure. So they found a stronger negative trend for a negative relationship of early life exposure to PM10 than later in life. Then a study by Roya Martinez from Mexico. They followed older children from age 8 until 11, and they found that with increasing NO2, the FEV1 decreases annually with 0.03 liters in girls and 0.02 liters in boys. Just gonna sip water. Then maybe the most influential study is the California Health Study. They looked at US children in 12 different communities across California. They followed these children from age 10 to age 18 and did pulmonary function measurements each year. And they found that with an increasing NO2 of 65 micrograms per cubic meter, that their lung function decreased by 0.09 liters for FVC and 0.1 liters for FEV1. And these results are also significant. What is also important about this study is they looked at the influence of relocating. So they followed the children that moved from a community, for instance, from a community with high exposure to PM10 to a community with a lower exposure, and you can see that their lung function growth recovers. So their lung function growth is getting better again, and if they move to a community with a higher exposure, that their lung function decreases over time. Lung function growth decreases over time. So in summary of this previous studies, they found a relationship often between traffic-related air pollution and lung function. The trend that it is a negative influence on lung function in both cross-sectional and longitudinal studies. But the number of studies is low, and this is why more research is needed and why we did our study. For our study, we used the data from the Canadian Asthma Primary Prevention Study, which is a birth cohort study. It was initiated in the early 1990s by Ellen Becker and Moira Chen Young. It is situated here in Vancouver, BC, and in Winnipeg, Manitoba. The study involved a sort of multifaceted intervention for children at high risk of developing asthma to hope to prevent them from developing asthma. They recruited mothers of high-risk infants in their third trimester of their pregnancy in Vancouver and Winnipeg. And they were at high risk because at least one first-degree relative had asthma, or they had 2 first-degree relatives with an IgE-mediated allergic disease. These families were randomized and placed into the control or the intervention group. The control group received usual care, and the intervention group had different measures to reduce exposure to house dust mite and pet allergens, avoidance of secondhand smoking, the encouragement of breastfeeding, and delayed solid foods. So again, 545 families were recruited, were placed into the control or the intervention group. The infants were born. There were some twins among them, and they were followed and assessed at age 1, 2, 7, and 15. For us, age 7 and 15 is very important because they did the pulmonary function test at this age. And for the people who are interested in it, on the right, there are the results of the intervention. And you can see that the children who received intervention were less likely to develop asthma. So back to our study. The goal was to contribute to the understanding of the relationship between traffic-related air pollution exposure and lung function. This study complements previous studies because it's done in a high-risk group. We have repeated measures of pulmonary function, and we have high-resolution spatial models of traffic-related air pollution. We'll get back to that. First, the health assessment. As I said before, the health assessment is done by spirometry. These show the results of our study population. You can see that lung function increases over time for both males and females, and that FVC values are often higher than FEV1, which makes sense because it is a bigger part of your lung volume. There's different covariates that influence lung function. As I said before, males are higher than females. The age is important, as you can see, and also race, weight, height, and others. Exposure is measured in this study by land use regression modeling. Previous studies often used dispersion modeling or just physical measurements. This study, or this method, is pretty new, and it involves, or it includes physical measurements as well as GIS measurements combined into a regression model that calculates individual exposure to NO2. So how is this done? Well, they selected different locations throughout Vancouver and Winnipeg. These locations have high variability of NO2 and high population densities. They chose a 2-week sampling period. They chose it because these 2 weeks represent the annual average best. They combined this with information about the roads. For instance, if they had road work on this road, and what kind of road was this? Is it a highway, or is the traffic density low? And this together made the land use regression model, which explains about 60 to 70% of the actual data. Well, these are the actual models for Vancouver and Winnipeg. You can see that the model for Vancouver includes the information about the type of roads, the density of the highways, the distance to the nearest highway, and the population density. And in Winnipeg, it includes the land use for industry, the road length of a highway, the road length of all roads, and the population density. And they both pretty well explain the actual data. There's a little bit, but it's okay. So here you can see the models plotted over both Vancouver and Winnipeg. And you can see that exposure is highest close to major roads and in city centers. These land use regression models cannot only be used to calculate exposure at one certain point in time, but it can also be used to calculate the exposure previously. This is done by adjusting for temporal trends, and therefore you can also calculate what your exposure was, for instance, a couple of years back. So this is done for our study population, and you can see that the exposure in Vancouver is significantly higher than it is in Winnipeg. So I'm sorry, but you have to move. No, it's okay. For the data analysis, I just requested the information of NO2 and the pulmonary function measurements that were done by my colleagues, and combined this with the additional covariates that influence this relationship. I organized this data by case and time and created some new variables, for instance, race, because we only had information out about the maternal and the paternal race, so I combined that into information about the child's race, and also some variables explaining the difference between age 15 and 7 were created. For instance, the difference in weight and the difference in height, something like that. They were added to the model if they influence pulmonary function with significantly. Here you can see some of the characteristics of the study population. I don't expect you to read all this, but we created 3 different groups. One group contained or had all the children in them who had NO2 measurements or NO2 calculated NO2 exposure values and pulmonary function at age 7, and the same one for age 15. And one group that had children in them that had pulmonary function measurements at both age 7 and age 15 to calculate the growth. The study contained a high proportion of males that were part of the intervention group, were Caucasian, high amount of people with asthma, with wheeze, breastfed, very active, typical for children, and high history, family history of asthma. Okay, so first the cross-sectional results. We did a linear regression analysis of the effects of NO2 on lung function at age 7 and age 15 separately. First, the results at age 7, you can see that increases in NO2 positively influence lung function. This is not what we've seen before, but could be explained because maybe we don't have some of the confounders in our model that that would make it negative, or because it's cross-sectionally, so it's comparing to 2 individuals instead of the longitudinal, which we talk about later. Something. Sorry, I have something in my eye. Yeah, so that could explain it. At age 15, you can see that at the main model we do find a negative relationship, and the minimally adjusted model we don't find it. We see a positive relationship, which is of course a finding as well, but this states the importance, again, of adding different confounders to the model. Not only sex, age, and weight and BMI might influence this relationship, but other confounders as well, and you can see that this changes the model. So the results we find at age 15 are sort of in concordance with what we saw in previous studies. Now the most important results, the relationship with lung function growth. Here you can see that both the minimally adjusted model and the main model show a negative relationship, although it's not significant. The values are higher than we saw at the previous studies. And we see that growth is decreased when NO2 is increased. So if we separate this out for males and females, we see that both for males and females, lung function growth is decreased with higher concentrations of NO2. Well, you might notice that we see 2 distinctive clusters. Well, that could be explained by Vancouver and Winnipeg. And still, even if we separate for these 2, we see a negative relationship for both, although the relationship is stronger in Winnipeg than it is in Vancouver. So to summarize the results, they suggest a negative relationship between traffic-related air pollution and lung function. There are some limitations of this study, which are the low number of participants. We only have 2 points in time, have the pulmonary function measurements, only at age 7 and 15. And for instance, CHS study had annually results of their pulmonary function. And we did not correct for short-term variability in air pollution and lung function. I don't know if you know, but for instance, at the day of the lung function test, air pollution levels were very high. This could influence the pulmonary test and therefore influence the relationship we find. Although the results were not significant, the effect, let's shift a little bit, that's okay. You can still read it, right? The impact may actually be pretty large. We see that results we find translate into a decrease of lung function growth of 12.9% for FEV1 and 7.8% in FVC. This might lead to a lower maximal lung volume, and that could have its effects later in life, because then you won't start at 100%, but you will start lower, and which lead to that you will reach critical levels earlier than you would have if you had 100% at the start. So as a conclusion of this all is that our study contributes to the relationship between traffic-related air pollution and lung function, and this relationship is negative, and therefore the evidence is growing, and I think it's time to act on it and limit our exposure. This can be done both spatially and uniformly by, for instance, decreasing the exhaust from cars or changing our road plans to minimize exposure. Well, that is it. Thank you all, and a special thanks for Mike, Chris, Hind, and Thayer, who made my stay more enjoyable.
Thanks. Really interesting study. I enjoyed that. I'm just curious though, do you have any insight as to why Vancouver NO2 levels are so much higher than Winnipeg's? I would have thought it the other way around.
I believe that most of it's because of the climate, maybe? No? Bigger city, okay.
Other questions?
I was wondering, when you were doing your regression model, you corrected for air conditioner. I was wondering what your thoughts are as to how it might actually influence the relationship.
Well, I based most of it on the previous research, so I would have to look it up why it was that I included that one. So if you want, I can look it up and email you about it.
Yeah, great.
I really enjoyed that. Thank you very much, Elise. It was nice to meet you this morning, too. I wanted you to, you had this population that was just generally described as vulnerable, but did you know something about their disease state as well, and did you include that in your model? Like whether they actually were atopic or had asthma? I didn't, maybe it was there and I just missed it.
Yeah, I included, well, it isn't shown, but I also did a separate analysis for asthmatics and non-asthmatics, if you want that. But I have included that in the model because I did it just yesterday. So, and actually, they both show a decrease for both asthmatics and non-asthmatics. Yeah, it was stronger in non-asthmatics than in asthmatics.
guess we're out of questions, and thanks very much, Elise, for an interesting study and a good report on it. And the best of luck with the rest of your studies.
Thank you.